So now we consider some more slightly complicated cases, which is the multi-loop circuit, because single loop circuit is too simple, which is not so practical in some case. So we try to learn the multi-loop circuit, and here the textbook introduced the junction rule, and I usually call it KCL, Kirchhoff current law. So the sum of a current entering any junction, the sum must be equals to the sum of current leaving that junction. So which means that, for example, for point B, the current going in this junction, for this case is I2 going in, is equals to I1 and I3 add together, which means that I2 should be equals to I1 plus I3. So this is going in. This is going in, this is going out. But usually try to distinguish what is going in, what is going out would be complicated. You can make mistakes from time to time. My habit is to assume all the current going outside, and then you add all of them together to be equals to 0. And because it doesn't really matter, you assume the current is going in any direction. If, for example, if you assume I1 is going in this direction, it can be positive, which means that the current really go in this direction. If you calculate that I1 is negative, which means that actually I1 is going upward. So it doesn't really matter how you assume the direction of the current. And in this case, I usually assume that the current is going outside from a loop, from a node to make my calculation, and then I will have smaller chance to make mistakes. So I make this as an example for point B. Assume that the voltage at this point is VB, and then assume that this VD, the point D, is a ground node. So VD is 0, and this is VB. So applying KCL at point B, would be something like the current going this way, and then we add all of them together to be 0. So for I3 is trivial VB over R3, because this is VB, this is 0. So VB minus 0 over R3. And for I1 would be, as long as this one is VB, so for this point should be VB plus E1. VB plus E1. And then this is VB plus E1, this is 0. So So the current of I1 should be VB plus E1 over R1. Maybe you can put a minus 0 in the numerator. And for this current from this way, as this one is VB, so for point C should be VB plus E2. VB plus E2. And then this is VB plus E2, this is 0. So the current going in that direction should be something like this. And then we add all of these three current together to be 0. So actually, if I want to match this to be in the figure, so actually this one is I3, this one is I1, but this one is actually minus I2. This one is actually minus I2. Okay, so finally we can find that we can group VB together, so we have R1 plus R2 plus R3. And then we move minus E1 R1. And then minus E2 R2. Ouch. E2 R2. Something like this. So finally, we can get that VB is minus E1 over R1 plus E2 over R2, or in parentheses, and then 1 over R1, 1 over R2, 1 over R3. If you like, you can simplify this fractional expression, but this is not the the point in this course. So another way to solve the same circuit for the previous method, in circuit theory we called it the node analysis. Node analysis. And this one we call the node equation. Actually, in circuit theory, we can also use the mesh analysis, or we can write the mesh equation. But this may be a little bit difficult to understand for you, but I just let you know so that, well, if you can understand, you can also applying this method to solve the circuit. Because some types of circuit, you use node analysis, then you can come up with simpler calculation. For some circuit, you use the mesh analysis, and then you can come up with simpler calculation. But for most of the case, both are similar. And in this method, it is not so easy to understand as in the previous case. So try to pay attention. So for the mesh analysis, we will assume the mesh current. We call it I1. I1 for this mesh. For this mesh, we assume the mesh current for this loop is I1, and for this loop, the mesh current is I2. If you like the mesh current to be in counterclockwise, it's okay, but likewise, I usually assume all the mesh current to be in the same direction, usually clockwise. So for mesh 1, we can write the mesh equation. So at this moment, you just ignore this. You ignore the I1, I2 given by the figure at this moment, and then we try to write the mesh equation. So first of all, we have the R1, so that from this point to that point, we have a voltage drop I1 R1, which is a voltage drop, and then from A to B, E is also a voltage drop. E1 is also a voltage drop. But for R3, we can see I1 going this way and I2 going this way. So for R3, this is a little bit tricky. It is influenced by both I1 and I2. So we have I1 minus I2. I1 in this direction, so that I1 R3 is the voltage drop. So it is positive for voltage drop, and then I2 going from this way to that way. So that from the point of view of I2, this is high, this is low. So we should minus I2 in this case. So for mesh 2, we do the stuff similarly. So we will have I2 minus I1 R3. We start from this case. We start from R3. So from the point of view of I2, this is a voltage drop. So I2 R3 is positive. I1 is in the opposite direction, so we minus I1 R3. And then from point B to point C, it is a voltage rising, so that we minus E2. And then for R2, it is also a voltage drop, so it is R2 I2, something like this. And in this case, we can also simplify this. We can try to solve I1 and I2. All the other stuff are the unknown. So we have two equations and we have two unknown with two equations. So then we can solve I1 and I2. And finally, we can know the current. I1, something like this. And the current going through I3, maybe in this direction. Maybe I can release the I3. So ignore this I1 and I2. And actually, if you want to know I3, it will be I3 in this direction going downward. It will be I1 is going downward, but I2 is going upward. So it will be something like this. And as long as you know all the current going this way and this way, and this way, then you can know the voltage at different node, as long as you would like to know. So the next is the resistance in parallel. Resistance in parallel. So this figure has 3 resistors in parallel. And then similar to series resistor in series, we want to change this part with a equivalent resistance. And then as long as we put all of them in a black box, we cannot distinguish this one and that one. Then we'll say that they are equivalent. So for the left-hand side case, we apply the KVL, KCL. We apply the KCL, and we know that I is actually equal to I1 plus I2 plus I3, something like this. So the I should be V over R1 plus V over R2 plus V over R3 for I1, I2, and R3, something like this. And for the right-hand side case, it is a simple one, which is I equals to V over REQ. V over REQ. So as long as they are equivalent, which means that these two I should be the same, and V is the same, so that 1 over R should be equals to this stuff, which means 1 over R EQ equals to 1 over R1 plus 1 over R2 plus 1 over R3. Or in a sentence, if multiple resistors are in parallel, then you take the sum of the inverse of the resistance, and then you take the inverse of the answer, will be the equivalent resistance. So in general, if n resistance in parallel, you calculate the R equivalent like this. This is the inverse of the R equivalent, and then you take the inverse, will be the REQ. So this is a simple comparison between the series and parallel resistor and capacitors. So for series resistor, we add all of them together. For parallel capacitor, we add all of the capacitance together. But for parallel resistor, we take the inverse and add all of them together, and then we take the inverse to the answer, to the sum, and then it will be REQ. And similarly for capacitor, series capacitor. So actually this one should be the same form with this one. This one has the same form with this one. Okay, let's see an example. A figure shows a multi-loop circuit containing 1 ideal battery and 4 resistors. So R1, R2, E, R3, R4. What is the current through the battery? So in this case, this circuit is pretty easy. So you can see that you see that for point B and point C, you have R2 and R3 are in parallel. Although R3 is in this direction, but actually it is actually the same as point B, point C, and then something like this, R2 and R3. So it is actually a series resistor. So first of all, R2 parallel R3. R2 parallel R3 is something like 20 times 30 over 20 plus 30. This is the simplest case because as long as you take the parallel resistance of two resistors, it is something like R1 plus R2, and then you take the inverse, so it finally it is something like R1 plus R2, R1 times R2 over R1 plus R2, something like this. So R2 plus parallel R3 should be 12 ohm, 12 ohm, and then the overall R equivalence is R1 plus R2 parallel R3 plus R4, which is 20 plus 12 plus 8, which is 40 ohm. 40 ohm. So finally, I is E over R equivalent, which is 12 volt over 40, which is 0.3 A, 0.3 ampere. So next, for part B, what is the current going through I2, R2? So I2 is this one. I3 is that one. So as long as we know that I is 0.3A, 0.3A, so VBC should be I times R2 parallel R3, which is 0.3 times 0.3 times 12, which is 3.6 volt. So in this case, I reapply the Ohm's law. I2 will be VBC over R2, which is 3.6 over 20. So it turns out to be 0.18 A dot V. 0.18 ampere. And for part C, what is the current I3? So I3 is nothing but VBC over R3. So it is 3.6 over 30, which is 0.12A. So I2 is 0.18A, and this one is 0.12A. This one is 0.3A. So they should satisfy the KCL. Which can be written as I equals to I2 plus I3, which is the KCL. So the next example is like this. Well, actually, you can use node analysis or mesh analysis for this example, but here maybe I try to use the mesh analysis. Because this example, this method is not so easy to understand. So I use it as an example to demonstrate this one. But for this case, I assume I2 counterclockwise. I1 is clockwise. So this I1 and this I1 matches, and this I2 and this I2 matches. So my assumption and the notation in the figure doesn't conflict with each other. So for mesh one, so we start from E1, from this point to that point, E1, and then this is the voltage going up, and then start to have voltage drop for I1, R1, voltage drop across this loop for this one and this one. So we have I1, R1 also. And E2 is also a voltage drop. So E2 is a plus sign. But for R2, the current should be I1 plus I2, R2. Because I1 is clockwise, so for R2 it should be positive, and for R2 counterclockwise, which means that for R2 in the same direction. So we have I1 plus I2 times R2. And for mesh 2, we start from here. So E2 is the voltage potential change is positive. So E2 should be equals to no, not this. Should be from here, starting from here. E2 is from here. So in this case, R1 should be positive. So we have I2 R1 plus I2 R1, and then E2 is a voltage drop. So positive sign on the right hand side. And for R2, it is similarly I1 plus I2 times R2. So we can try to simplify the equation 1 to be like this: E1 minus E2 equals to 2R1 plus R2 times I1 plus I2 R2. So you can see that you have R1 to R1, and then R2 times I1, so that we have R2 here, and then we have R2 times I2, so that we have this term. And for equation 2, for mesh 2, we have these two to be cancelled. So the left hand side is 0 equals to R2 I1 plus 2R1 plus R2 I2, something like this. So I1 and I2 are unknown variable, all the other are known variable. So that we have two unknowns with two equations. Two equations with two unknowns, so then we can solve I1 and I2, and then we substitute the number in it. So 1 will be 3 minus 6 equals to 2 times 2 plus 4I1 plus 4I2. And the second one will be 0 equals to 4I1 plus 2 times 2 plus 4I2, something like this. And then finally, you can find that I1 is actually minus 0.5A and I2 equals to 0.25A. 0.25A. Okay. So actually, you can find I1 and I2. So our I1 matches this I1 and I2. And finally, I3 should be nothing but I1 plus I2, which is minus 0.5 plus 0.25, which is minus 0.25A. Minus 0.25A. Which means that I1 should be actually going this way. I1 should be actually going this way, and then this should be a plus value because we calculate that I1 is minus 0.5A. So as long as it is positive, it should be going this way, and I2 is going this way. I2 going this way. And for I3, it is negative, so I3 is going upward. I3 is going upward when we consider the polarity, the sign of the answer. So next we talk about the ammeter and the voltmeter. So this is some sort of equipment to measure the current in a path or a voltage between 2 points. So A is a symbol stand for the ammeter, and this one V is the symbol stand for the voltmeter. So we need to consider that the current, the ammeter should be in series with the current we want to measure, and the voltage meter should connect it to the 2 point we want to measure the voltage difference, and this is not difficult to imagine. So ammeter is to measure the current in a wire, and the characteristic for the ammeter is that it is essential that the resistance of the ammeter should be very, very small or much smaller than the resistance of the path, because you know that the ammeter is in series with this path, so the current going through I should be VDC. No, not VD. Yeah, VCD minus E over R2 plus small r. R2 plus small r. If A has a large resistance, it will influence the current of the circuit. Then actually, originally you want to measure the current, but actually when you in series with the circuit and then you eventually influence the current, then this is not so good. So the point here is that the resistance of the current meter should be much smaller than other resistance in the circuit. Otherwise, very presence of meter will change the current to be measured. As long as this one has another resistance RA, then the current will become VCD minus E over R2 plus R plus RA. Then you will influence the operation of the circuit. And for the voltage meter, the resistance RV should be much larger than the resistance of any circuit of the element. For this case, this voltage meter is parallel with this R1. So the best case is the resistance of the voltmeter is infinity. Because they are in parallel, if it is so you can consider you have a RV here, and there's no current going through this path, and RV is in parallel with this R1. If RV is very large or ideally tends to infinity, then there will be no current going through this path, and the circuit will just look like there's nothing influence it, and the operation of the circuit doesn't really change. Likewise, for this case, if this one RA is ideally zero, then it will not influence the current of the whole circuit. But if RV is not large enough, then there will be some current going in this path. Then it will actually change the voltage between point C and D. Then it will not be so good. So the next part is the RC circuit. So so let's talk about the conclusion first. In the textbooks, it tells you that if you want to charge a capacitor, originally the capacitor is initially uncharged. So in the previous lecture, I talked about solving the ODE. So we talk about the initial condition, and this is actually the initial condition. It tells you that the capacitor is initially uncharged, which means that there are no charges stored at the capacitor. So to charge it, we should close the switch S on point A, which means that which means that the switch go to point A, and then the EMF will connect it to this so-called RC circuit. So this completes the RC circuit consisting of a capacitor, ideal battery, EMF E, and a resistor R. So the current will be so this is at point t equals to 0. Then the current. So this is I. The current will be E over R times E to the minus T over RC power, something like this. And RC is what we call the capacitive time constant. So this time constant characterizes how fast the capacitor can be charged. It can never be charged to E, but it will gradually approach E. Or I will gradually approach. I will gradually decay to 0. And actually, this should be Q. This should be Q, or VC. VC will be E times 1 minus E2 minus T over RC power, which means that when T become larger and larger, E to the minus infinity will be 0, which means that VC will approach VC, or VC will approach E when T is very large. Usually, we will assume that when T is larger than 5 tau, then it will be then this two term is approximately 0, because you can consider E to the minus 5 should be a very, very small number when you try to calculate use a calculator to calculate this value. This should be very, very small. And then we will assume VC is approximately equal to E in an engineering sense. So I will try to derive equation 27.34 and 27.35. So we have EMF E, and then we have RC, and then the switch is closed at T equals to 0. This is ground node, okay, and the voltage across the capacitor is VC. The current is I. So in this case, applying the KVL, we have E equals IR plus VC. So going from this point, going up E, I is clockwise, so voltage drop for the resistor. So IR, and then VC is also voltage drop. This is plus, this is minus. And for the capacitor, we know that we should know that I equals to C dVC dt. Because in chapter 25 we know that for the capacitor, Q equals to CV, okay, or VC in this case. V or VC is just a variable name. It doesn't matter. So in this case, we take the derivative with respect to time on both sides, as C is a constant. So we can write that dQ dt equals to C dVC dt. And in chapter 26, we know that dq dt is actually I. So finally, we get this expression. So this is very we will frequently use this in the next chapter. So for this one, we take the derivative. Do we take the derivative? Oh no, I can just substitute I into here. So that we have RC, R times I is this one. So we have C dVc dt plus Vc equals to E equals to V. So in this case, we just substitute I equals to dVc dt into the star equation, and then we can multiply RC. So cancel. So we have dVc dt plus 1 over RC Vc equals to E over RC. Okay. So so don't forget the initial condition is initially uncharged, which means that Vc0 should be 0 volt or 0. So the first thing to solve this differential equation is that we solve the left hand side to be equals to 0. So the characteristic of it is S plus 1 over RC equals to 0, which means that Vc, the homogeneous solution is A times exponential to us. Exponential to minus T over RC. So we have this term, and then next we assume Vc, the particular solution, is a constant, because this is a constant which is a zero order polynomial, so that we assume Vcp is a constant, and then we substitute Vc equals to B into here, so that the first derivative of B is 0, and then plus 1 over RC times B to be E over RC, so that we have B to be E. So very simple. So that we can write that Vc is Vcc plus Vcp, which is A exponential to minus T over RC plus E. And then we know that Vc0 is 0, which should be this one. We substitute T equals to 0, which is A, because E to the 0 power is A, plus E. So A should be negative E. In this case, we know that Vc should be E 1 minus E to the minus T over RC power. So we can derive this one. And next, we know that I equals C dVc dt. So it is nothing but taking the derivative. Of you can write it as E minus E exponential to minus T over RC power. So this is a constant. Taking the derivative of it is just 0. And taking the derivative of this term will be minus e, and then take the derivative of the exponential function is the exponential function is of itself, and then don't forget the chain rule. We need to take the derivative of this one, which will be minus 1 over RC. Minus 1 over RC. So that C and C cancel. And we have two negative signs, so we have plus E over R, e to the minus T over RC power. So in this case, we can derive this one. And actually, for this case, after the capacitor is charged by the and then the switch, after the capacitor is charged, and then the switch turn to point B, so the charge will be, the capacitor will be discharged, and actually the current will be something like this, and VC will be something like this. So in this case, we also can draw the circuit like this. C, this is BC, and so in this case, still we write T equals to 0. So in this case, we write we use the KVL. So we can also write that dBc dt plus 1 over RC VC equals to 0. Because at this time we don't have the EMF, so no EMF, so on the right hand side it is only 0. But in the previous case, we have E over RC on the right hand side, because in this case we have ideal voltage source there, but here we don't have a EMF, so there's a 0 on the right hand side. So in this case, and the initial condition should be V0. It tells you that the capacitor is fully charged to V0. So Vc of 0 is V0. So in this case, Vc is nothing but the homogeneous equation. So it will be A times e to the minus t over RC power. And we substitute t to be 0. So A, and then the initial condition is V0. So A is V0. In this case, Vc of t should be V0 times exponential to minus t over RC power. So in this case, we can derive this one, and likewise, we can derive I equals to C dVc dt. So which is equal to C times the derivative of this one. So first V0, and then the derivative of the exponential function, which is itself. And then the chain rule, we take the derivative of the exponent. So it is 1 minus 1 over RC. So finally, C and C cancel. C and C cancel. We have one negative sign, so I would be V minus V0 over R multiplied by minus e to the minus T over RC power, which means that as long as it is discharging, the current is going this way, counterclockwise. So in this case, we derive this equation. And so this is all the content in this chapter. This is all the content in chapter 27.